All right, here we go. We are going to plow through some basics here. I'm going to do this really fast. If you need more, go back and rewatch one of the honors videos from last year. This one's going to be short, but buckle up because the next one's pretty long. So just a heads up. All right, here we go. So we're going to learn right now about, so this whole chapter is about work and energy, right? And in this video specifically, we're going to learn about different types of energy. This should literally all be review, so it's going to be very quick. All right, so quick reminder, kinetic energy is energy of a moving object. Anything that's moving has kinetic energy. If it's not moving, it has no kinetic energy. All right, remember, the kinetic energy depends on the velocity of the object. The faster it's moving, the more kinetic energy it has. And it depends on the mass. The more mass it has, the more kinetic energy it has, as long as it's moving, okay? So we measure energy in joules. Remember, 1 joule, we abbreviate with a J. A joule is the same as a kilogram times a meter per second squared. All right? If you want to calculate your kinetic energy, it is 1/2 mv squared. All right, we did this a ton last year. I'm not even going to do an example. Like I said, watch the honors videos if you need. All right, gravitational potential energy. All right, so this is one quick thing that's new. Notation. So most college physics books, instead of using PE for potential energy, they use the capital letter U. Can't draw capital U, apparently. All right. So I will kind of oscillate between the two. I really like GPE, especially for a first-year course, an honors course, just because this U is so non-intuitive. But this year I'm going to kind of use both, so just kind of get used to it, okay? All right, so gravitational potential energy is potential energy that an object has stored due to its separation from some object, usually the Earth, to which it has some gravitational attraction. All right, so gravitational potential energy, at least for now, can be calculated by taking the mass of the object, multiplying it by g, which remember is positive 9.8, and multiplying it by the vertical position of the object. Last year we used h, okay? And we talked a ton last year about the fact that the gravitational potential energy could be converted into kinetic energy, right, if you drop the object, okay? But we'll talk about that more later on. Something we didn't talk about is this. So when we talk about potential energy, it's always referred to as stored energy. So like when you talk about, you know, a battery, that has stored energy, right? And where's energy stored? In the battery, right? So it's important that you identify where the energy is stored, okay? And so it turns out that the gravitational potential energy is stored in the gravitational field. All right, now because we didn't do a ton of electricity last year, we didn't do a ton about fields. But I guess what I want to make sure that you understand is this, that if you're talking about, you know, the Earth and a box of gummy bears, and we talk about the gravitational potential energy that the box of gummy bears has, technically speaking, the gravitational potential energy doesn't belong to the box of gummy bears, it belongs to the box and Earth system, because there's a mutual attraction between these two objects. So the energy isn't necessarily the gummy bears, it's not necessarily the Earth's, it belongs to the gummy bear Earth system, which creates a field, okay? So anyway, if that didn't make sense, it honestly is not going to be that big of a deal until you get to electric fields. So you will learn about that in physics 2. All right, so another type of potential energy, elastic potential energy. So I'll usually use E to represent elastic, okay? So elastic potential energy or elastic potential energy is potential energy that an object has stored due to an elastic object being either stretched or smooshed, okay? The physicsy term for this would be placed under tension or placed under compression, okay? Usually this year we're going to consider the elastic potential energy of a spring which follows Hooke's law. If that is not clear, I don't know if you remember this from last year, but a spring that follows Hooke's law is called an ideal spring. Okay, a spring that follows Hooke's law is called an ideal spring. So if you don't remember, This is Hooke's law. The elastic force exerted by a spring is equal to negative kx, where k is not defined anywhere on the screen, so we should probably do that real quick. Insert blank page. All right, so k is called the spring constant. Every ideal spring has what's called a spring constant. All right, and the spring constant is a measure of the amount of force that the spring will exert per unit of displacement, per unit that you either stretch or smoosh it. Okay? So, for example, if I give you a spring that has a constant of 5 newtons per meter, it means for every meter you stretch the spring, it'll exert another 5 newtons of force. Okay? All right. And so based on that, then, you can calculate your elastic potential energy. Elastic potential energy is 1/2 kx squared. Okay, where k is your spring constant, x is how much you have either stretched or smushed it from its relaxed state. Okay, please notice that the direction of the force is always opposite the direction of the displacement, right? Because if I have a spring that looks, so suppose I've got a spring and a box that's sitting here, okay? So it's in its equilibrium position, right? And then I take the spring and I stretch it. Then my displacement was this way, and the force of the spring is going to want to restore it to its equilibrium point. So here's the elastic force, or the spring force, okay? So notice they are opposite directions, which is why there's a negative sign there. Okay? So, I think that's it. Is that it? Whoa. Yep. All right, there you go. So, like I said, if you need more review than that, please go back and watch some of the honors videos. Okay? Very good. How do I stop this thing? Jane, get me off this thing.